Let's start with a pre-built diagram providing some data sources and visualization components. We have a live camera, followed by a generic objects detection component. In order to add more interesting streams, we prepared a player component providing data from an automotive recording. It just emulates the presence of real sensors. Among others, we will use front camera data as an H.264 stream, rear camera data, GNSS data as an NMEA stream, and a corresponding decoder for the latitude and longitude, and a CAN bus data, which, after decoding, provides the speed and steering angle signals. All these streams are connected to the dashboard component, which publishes them towards a licked-blick visualization panel. Let's run this diagram to see what it all looks like. We can see in licked-blick the 3 video streams, our GNSS position on a map, and our speed and steering signals from the CAN bus property plotted. Let's come to the point: smart recording. First, we need a recorder component, of course. Then, let's add a pre-trigger buffering component. Connecting these streams directly to the recorder would end up in continuous recording. But we want to record those streams only around certain events. Let's say 15 seconds before and 10 seconds after those events. This component will buffer the incoming data in a circular buffer of fixed duration, then forward the buffered data to its outputs upon reception of a data sample on its trigger input. Then it will keep on transferring the incoming data for some time after the reception of the trigger event. Therefore, only the data from the X seconds before and the Y seconds after the triggering event will be forwarded to the recorder component and saved to disk. Let's first configure the component to manage 7 streams. We can configure the output names. The buffer time and the release time properties determine respectively the duration of data that will be kept in memory and transferred to the outputs upon reception of a triggering event, and the duration of data that will keep on being transferred to the outputs after each triggering event. In short, that means we will record 15 seconds before and 10 seconds after each triggering event. Let's record the 3 video streams, the GNSS position, the 2 CAN signals, and the triggering events as well. Now we connect the data streams to the PTB component on their corresponding inputs. We can now safely connect the PTB outputs to the recorder component and choose a compatible recording file format for each of those. Note that we need here to check the never skipping option. Indeed, we have to prevent FIFO overflows between the PTB and the recorder components. With FIFO reader inputs at the recorder, such FIFO overflows would be likely to occur due to the fact that, upon trigger, the PTB component will publish all the buffered data to its outputs as fast as possible. This creates bursts on the PTB outputs, which the recorder cannot dump to disk so fast. The never-skipping reader policy on the recorder inputs will block the PTB component, if necessary, instead of allowing data drops due to FIFO overflows that would have occurred with standard FIFO reader inputs. This is one of the rare cases where the never-skipping reader mode is necessary in a real-time diagram. We now need to define the events that will trigger the recording. Let's first capture the sequences where the car stops, for instance. We will use a condition component. The condition expression will be speed lower than 2. That creates a speed input. We want this component to output a sample when the condition becomes true. That means when the value received on the speed input goes from above 2 to below 2. We now just have to connect the speed signal value to the condition component speed input and the condition output to the trigger input of the PTB component. While we are at it, the triggering event output is also recorded via input_6 on the PTB component and also connected to the GUI panel. That's it. Let's run. Let's split the screen for both the licked-blick panel and the RTMaps diagram. The licked-blick panel allows to visualize the various data streams. Keep an eye on the speed gauge or the speed plot at the bottom. Also keep an eye on the RTMaps console view. Arriving at the roundabout, the vehicle slows down until the speed gets below 2 kilometers per hour and our event is triggered. The PTB component starts dumping the last buffered 15 seconds of data to its outputs for the recorder. Then 10 seconds after the event, it stops forwarding the incoming streams. We can now stop the execution and take a look at our recorded files. The rec file starts at second 35. That means 6,175 seconds, or 1 hour 42 minutes 55 seconds in the played back dataset. So, exactly 15 seconds before our event. We can see the entry for our triggering event at second 50. Then the recording lasts until 1 minute, so exactly 25 seconds after the recording start, as expected. The secondary files contain the data from the recorded streams for those 25 seconds only. Let's open the front camera AVI file to double-check. It starts when we approach the roundabout. At second 15, the ego vehicle stops. Then it contains an additional 10 seconds of video data. Let's see how we can add more events of other kinds that would also trigger the recording. Manual triggering. We add a new condition component connected to the keyboard component and have it check the pressed key code in order to constitute a manual triggering event, for instance. When the received value is 71, then the condition component will output a sample with value 2. A multiplexer component will allow to combine these two events onto a single output to connect to the PTB component as trigger source. Object detection from computer vision. We also prepared a short Python script that can filter the detected objects from the YOLO AI algorithm and generate an event whenever a smartphone is detected in the image. Let's take a look at the script. It will publish value 3 when one of the received 2D objects has an ID of 67. So those 3 event sources are given different identifiers. The vehicle stopped event is 1, G, key press is 2, and a detected smartphone would generate a 3. It's time to run our application. Watch the Events lamp in the visualization panel and the RTMaps console view. Showing a smartphone to the camera triggers the recording. Pressing the G key also triggers a new recording sequence. The vehicle stops at the roundabout, which also triggers the recording. Eventually, let's combine these features with the chunked recording capability so that the recorder closes its recording at the end of each sequence and creates a new one. The status output of the PTB component tells us when all data has been published on the outputs after each triggered sequence. Let's then add a new condition component downstream and trigger the RTMaps command recfile_1.split. The split command on the recorder will shut down and restart the component right away, hence closing the current sequence and creating a new set of files. We introduce a 1-second delay to make sure that the recorder had enough time to dump to disk any pending data samples in the PTB output buffers. Last but not least, chunked recording requires to check the append record start time to recordings to avoid a folder naming conflict at each split operation. Now, let's run. First event is a smartphone detection. Note that 10 seconds after this event, the stop dumping message tells us the recording sequence is finished and the recfile_1.split command is correctly applied. The second event happens when the car stops at the roundabout. Same sequence. Start dumping data, which triggers the dump of the previous 15 seconds to disk, then 10 seconds later, stop dumping, and closing the current set of recorded files for opening a new one. At 1 hour 43 minutes and 48 seconds is the key press event, same behavior as for the two other events. And another phone detection event. See the state transitions in the visualization panel. The event IDs that triggered the recording session are shown here. This session created 5 folders, one for each of our 4 events and a last 5th one for preparing the files for a new event that never came, so it will remain empty. In the first folder, the recorded driver video properly shows the smartphone at second 15 and lasts 25 seconds as expected. The other files contain the corresponding data for the other data streams. In the second folder, the front cam video properly shows the vehicle stopping at the roundabout at second 15 and also lasts 25 seconds as expected. The fourth folder front video lasts 34 seconds instead of 25. This is because the sequence triggered by the last phone detection event has been concatenated with a low-speed event which occurred within 10 seconds after the phone detection. Therefore, the release duration is extended, so we get 10 seconds of recording after the last event occurrence. Hope you liked this video. In less than 20 minutes, we configured a complete smart logging application, combining events generated out of combust data, computer vision, and manual triggering. RTag, a live tagging app for manual annotation, could also take part in this smart recording process. Stay tuned. We will address it in a future video. For complementary topics around smart recording, check out our AI-powered cloud-based data management framework for managing your large amounts of recorded sensor data in the most efficient way. Thanks for watching. Don't forget to subscribe and see you in the next RTMaps video tutorial.